All right. So we had left off going through kind of the generic mechanism of nucleophilic aromatic substitutions, right? And we said that you've got your aromatic ring, you have your electron withdrawing group with a halide, you have your nucleophile. Your nucleophile adds to the carbon that has the halogen, kicks electrons over. And then these electrons come down and push your halide out. Makes your X minus. Right? And we said that the first step is the slow step. Second step is the fast step. First step is because it's the slow step, it's the rate determining step. The addition of the nucleophile to the carbon that has the halogen, this is called an Ipso attack. Ipso basically just like a fancy term for you're attacking a carbon that already has a substituent on the aromatic ring. So you're kind of adding two things to the same carbon. So that first step is an Ipso attack when you add the nucleophile to that. All right. Now, we said that the first step being the slow step, anything we do that speeds up the first step is going to speed up the overall rate of the reaction, right? So anything we can do to make that first step go faster makes the whole reaction go faster. The easiest thing to do is to change the halide. So more electronegative halides increase the rate of the reaction. All right, so this is 100% exactly opposite what we had for like SN2 reaction. So our fastest halide for these is fluoride, is the fastest. Then chlorine, then bromine, then iodide. Right, so this has nothing to do with how good of a leaving group these halogens are. It's all about how electronegative they are, how positive they make the carbon that is that the halide is bonded to. Right, fluorine's really electronegative. Right, so it's going to make this carbon right here really positive. Right, it's going to have a big positive charge on that carbon. Iodide is significantly less electronegative, so it's going to make this carbon itty bitty positive. Right, if you're the nucleophile, right, the nucleophile's job is to add to the most positive thing it can add to, right? So are you going to rather add to the carbon that's got the fluoride on it, it's a big positive, or the carbon that has the iodide on it, that's still going to be itty bitty teeny tiny positive? You're going to want to add to the most positive carbon that you can, right? So even though fluoride is a trash leaving group, it goes faster because what determines how fast this reaction is isn't how easy it is for the fluoride to be knocked off, or the halide in general to be knocked off. Instead, what matters is how quickly the nucleophile adds to that carbon, right? Because once we, I'm going to go back a slide. Right? Once we get here, as soon as we get to this compound, the halide's going to come off, right? Because the molecule is just going to have the electrons come back down and spit off a halogen so that it can get back to being aromatic. So it doesn't matter what the halogen is, it's gone, right? So it's just making this first step faster, and by being more electronegative, making your carbon that you're bonded to more positive, speeds up the first step of the reaction. So far, so good? All right. So I had mentioned that it's important for the halide and the electron withdrawing group to be ortho-para to one another. I said that was an important thing to remember. So let me actually draw a little bit more, be a little bit more detailed here. We'll actually draw an electron withdrawing group. They should. They will work, particularly if you have multiple electron withdrawing groups. They'll work if they're meta, but they work way better if they're ortho-para, and here's why. Right? So generic we'll do generic nucleophile again. Right? So I add to this carbon, push electrons over. When you're ortho or para to your electron withdrawing group, your negative charge ends up on the carbon that's bonded to the electron withdrawing group, which means that you can draw resonance structures where this negative charge goes out onto the electron withdrawing group. Right, so the electron withdrawing group can help stabilize the negative charge that you make in your intermediate through resonance, right? It can pull those electrons out of the ring and give the electrons an extra place to go. So this is true when their groups are ortho. It's true when they're para. Right, we'll have an extra resonance structure here, but it'll be fine. It's true when they're para. Great, so I can draw a resonance structure where I get my negative charge on the carbon that has the electron withdrawing group. Right, and then I can draw the resonance structure where those electrons go out on the electron withdrawing group. Right, so here, I will draw this arrow. There you go. And then this will come out. Right, so when they're ortho and para, the electron withdrawing group is helping to stabilize the negative charge. Right. When the electron withdrawing group and the halide are meta to one another, you end up skipping over the carbon that has the electron withdrawing group with your negative charge. So now if you're meta, I'll draw it the other way. If you're meta, right, you add your nucleophile, that part's still the same. right? You never get to draw a resonance structure where your negative charge is on the same carbon as the electron withdrawing group. So when they're ortho-para, the electron withdrawing group is helping to stabilize the negative charge you generate through resonance, right? You can always draw a resonance structure where the electron withdrawing group sucks the electrons out of the ring onto itself. When you have your electron withdrawing group meta, you're really just hoping that it's electron withdrawing enough that it makes the ring positive enough that it can hold a negative charge, but the electron withdrawing group itself is not helping to stabilize that charge. It's just like, I'm going to make the ring positive, and I hope it's positive enough that they can take a negative charge. If you add more electron withdrawing groups to the ring, it's fine if they're like meta. They still work. These reactions still work. But they work best when they're ortho-para because your electron withdrawing group is actively stabilizing that negative charge by giving it a place to go through resonance. Reasonable? Seems okay? Makes sense? Hopefully, maybe. Okay, so let's do some like examples where I have a little bit more than just like generic nucleophile. Right. So we have our electron withdrawing group. We have, say, a chlorine, and then we have a nucleophile. So these are kind of your SN2 type nucleophiles that we had from organic 1, right? So these are always going to be charged. It's always going to be like a metal and something charged is what's going to be your nucleophile. Usually oxygens or sulfurs are the most common nucleophiles, right? All you're going to do is replace your halogen with the negatively charged atom and everything attached to it, right? So if you remember, we can draw our little line. The metal is positively charged. The thing the metal is bonded to is negatively charged. So we're just going to put the oxygen with its methyl group in place of the chlorine. And that is going to be our product. You can do it with alkoxide, so oxygen's bonded to carbons. You can do it with hydroxide. Same deal, you're just going to end up with an OH on here. You can do this with sulfurs. Right, so S-ethyl O2. S-ethyl, there we go. And I can like swap around the counter ions, right? There's no reason that it has to be sodium for an alkoxide, lithium for hydroxide, right? So it's pretty easy for me to, goes to the other page. I have like potassium hydroxide or Lithium F oxide. Right. Another thing is a lot of people will get so locked into things being ortho para directing that they like kind of mix it up. Ortho para directing stuff is for electrophilic aromatic substitution. This is nucleophilic aromatic substitution. So you don't have to worry about any of that stuff. You're just going to replace, if you've got electron withdrawing group and halogen on your molecule, right? So you have whatever your electron withdrawing group is, and you have a halide, right? And a nucleophile. You're just replacing the halide with the nucleophile, right? You don't have to worry about, well, a ketone is meta-directing. No, that doesn't matter here, right? All that matters is that you're just replacing your halogen with your nucleophile. Right, so you just find your halide and you replace it with your nucleophile and call it good. I'm missing a methyl? I'm missing a methyl. Oh no.
The shame! The shame! The shame!
There you go. I feel shame. I'll put myself in the corner. Okay, gotta move on now. Okay. So next thing are benzyne reactions. All right, the first thing is I got to show you what a benzyne is. So benzynes are a benzene with a triple bond. So you've got a benzene that has a triple bond, and then these are very unstable. You can't isolate them. Basically, you make them and they react in solution. So you make this, you don't have a chance to isolate it, it's going to react with whatever in the solution that made it. You're going to have a reaction with it. So you can make these a couple different ways, and depending on how you make them, that kind of changes what products you can make. So the first way you can make a benzyne is just with base. So this is with a halobenzene and hydroxide or alkoxide. Right, so you've got, say, a halogen and then like NaOH and heat. So there's no electron withdrawing group on this molecule, so you can't do a nucleophilic aromatic substitution. The only thing available for this base to do is to remove a hydrogen and generate the benzyne. So you make like lithium or sodium chloride and water, right? Now this benzyne I'm not going to be able to isolate it. It's going to react with whatever in solution. So there's a bunch of hydroxide in solution, right? I used a bunch of base to make the solution basic enough to remove the hydrogen. So what happens is this benzyne is going to react with the hydroxide. I don't know why I picked green there. And you're going to make phenol, and then you have like water that you generated, and you can pick off a proton off of water. Boop. To make your phenol. Right, but I never have a chance to isolate my benzyne to add anything else to it. I just have to add the hydroxide that I used to make the benzyne. Now, you might be wondering or remembering that I taught you one very important thing with alkynes in Organic 1, and that is you're not allowed to draw bent alkynes, right? This is one of the exceptions. Like, these things exist, but they're super not happy about having a bent alkyne. So that's why they're so reactive, is you make them and the bond angles are all messed up and they're super reactive and they're just like, please kill me. Please just end it. And so they're like Mr. Meeseeks. Existence is pain.
Existence is pain to a Meeseeks, Jerry.
So just please end it. Just add to me. Hopefully you've all watched Rick and Morty. Peak TV. Come on now. All right. All right. So they just want to react. You make them, they're bent alkynes, they're not happy about it, and they get added to. So this is an okay way to make a phenol, but there is a bit of a problem. Right? This works great if your benzyne that you're going to make is going to be symmetrical. Right? So I've got my, say, like potassium hydroxide, me heat it. I have my benzyne that I make. Right? Intermediate. And my hydroxide adds to that. I can add to either side of my benzyne, right? Both sides of the benzyne are equally reactive. Whichever end of the benzyne, in this case top and bottom, that I get by faster, or the hydroxide is closer to, is the side that's going to react. Right? There's no selectivity there. Here it doesn't matter, right? Because my benzyne's symmetrical, so I only ever make one product. Right? I make this, or I make this, but they're the same thing, right? So it doesn't matter. If your benzyne isn't symmetrical, you're going to get a mixture of products. Right? So let's say we had just ortho-bromo-toluene. Same deal. Right? I get my benzyne. Right? Oop. Here. Get my benzyne intermediate. Can't isolate it. I'm going to react with my hydroxide. Right? I can add to the top, or I can add to the bottom. And that's going to give me two different products. Right? If I add to the top, I'm going to get the ortho product. Right? If I follow the red line, I get the red product. If I follow the green line, I get the meta product. All right, you get two different products. So a lot of times with benzynes, if you haven't specifically set up what your starting material is going to be so that your benzyne is going to be symmetrical, you're going to get multiple products. Right, so it's kind of a shortcoming of these reactions, is you have to make sure that the benzyne you're going to get isn't going to produce multiple products. You can also have situations where you'll generate 3 products in one reaction, right? So, sure. Sure, no problem. Right, so we'll use something slightly different. But we'll use an alkoxide. Right, here I can make 2 different benzynes. Right, because I have a hydrogen here, and I have a hydrogen here. So I can make blue benzyne, or sorry, green benzyne, I watched a lot of Sesame Street in black and white as a kid, so that's why the colors there were a little sketch. I'm that old. Right, so now there's carbon 1 you can add to. I'll make it orange. 1, 2. Right, so there are 3 different carbons you can add to because you have 2 different benzynes you can generate. So sometimes you just end up making like a mess and you just make a ton of products, right? You'll add methoxy up here and you'll get this. You'll add methoxy, so this is 1. 2. 3. We're just gonna pretend that green and red, when they mix together, make blue. We'll just pretend. Right, so you have to be mindful of when you pick your starting materials that you're only going to make 1 product. My goal, barring me having a stroke, is to make sure that if I give you a problem with a benzyne, that you're only going to make 1 product. Right? The benzyne will be set up in such a way that you aren't going to get multiple products. So it'll be easy for you to know what you're supposed to get. So stuff like, like I've drawn before, so stuff like this where there's only 1 benzyne possible. I can throw some extra stuff on it, but at the end of the day, you're only getting one product. You're only getting 1 benzyne. Oh, should throw the heat on there. There we go. All right, so you're only going to make 1 thing because there's only 1 benzyne that you can make. Right, I can make this benzyne right here. And the benzyne is symmetrical, right? It doesn't matter if I add to the top or the bottom. I get the same product in the end. So that is at least my goal. Again, barring me like stroking out. So we can add oxygens and make phenols and ethers. We can also do this with amine bases, which is basically the same thing. Right, so halobenzene and azide. So you can, or amide, I don't know. This is the second way, numero dos. It's basically the same thing, but now you have, like, instead of an oxygen, you have amines. But you're going to do the same thing in the end. The amine is acting as a base to make the benzyne. And then it adds to the benzyne.
The question was, do I need to add heat like I did for the oxygen ones?
You do not. You can have heat. Either way is reasonable. But it's not necessary because nitrogen is a better base than oxygen. So you can do it with simple, like, just ammonia bases, or you could have some groups on your nitrogen. Oops, too far. So you could have you could have like lithium and like dimethyl, right? And you could end up with 2 methyl groups on your nitrogen in your aniline product. So you're able to have some substitution on your nitrogen.
I was asked what the difference between the mechanism of the oxygen examples and these nitrogen examples were.
There isn't one, effectively, right? So here your amine base is going to grab a hydrogen, yoink, 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 make your benzyne. Let me draw it the other way. Other resonance structure looks nicer. Right? And then you're going to have your amine add to the benzyne. And then you'll have your negative charge, your carbanion, grab a hydrogen from your amine, from your conjugate acid that you made from having the amine remove the proton, and get to the product. So it's effectively the same mechanism. You just swap a nitrogen for an oxygen, but it's doing the exact same thing. Nitrogen's a little bit better of a base, so you don't necessarily have to heat it as much because nitrogen's willing to do that work for you. Cool. The third way you can make benzynes, I should write the guy's name down, but it's triflates and silanes. So here you have to kind of do a little bit of work beforehand to set the benzene up to make a benzyne. Right, so you're going to have OTF. This is the abbreviation for a triflate. And a triflate is just a really good leaving group, really good. And then you're going to have some sort of silicon. So you have a silane. Right? So you're going to have a silicon with 3 carbon groups on it, usually methyls. And then you're going to add F minus, add fluoride. And this will make a benzyne. And the benzyne can only be formed between where the silicon and the triflate are. So you always know what benzyne you're going to make because you know where your triflate and your silane were to start with. Right, so you can just look at it, you know exactly where the benzyne is going to go. So you only ever make one benzyne. So you eliminate the problem where you can make multiple benzynes. You still have the issue that the top and the bottom of the benzyne, right, either end, are both super reactive. But you eliminate the issue of making 2 benzynes when you just treat a halide with base. What's nice about this mechanism or this method is nothing that is in the reaction reacts with benzyne. So then you can add other nucleophiles to your benzyne after you generate it. So what ends up happening is I'll draw some stuff out here. So a triflate looks like this. And then we'll pick a silicon. We'll do 3 methyl groups. It's the easiest one. So when you have a fluoride, silicon loves fluorine more than any other element on the periodic table. So it will give up other bonds to make bonds with fluorine. So we'll add the fluorine to silicon. And silicon will end up with a negative charge on it. Now, silicon doesn't want to have this negative charge. It would much rather just have 4 bonds, but it's not going to give up its bond to fluorine now. It's got this bond to fluorine, it's done. You're not getting it off, the fluorine off the silicon. So what happens is it's got to have some way that it can get rid of some electrons so it can go back to being neutral. And the best thing for it to do is to have its electrons come down and push the triflate off of the aromatic ring. So you have this really good leaving group beside it, so it's like, fine, take my electrons and push that thing off. So that gets you your benzyne, plus you get this trimethyl silofluoride, which isn't going to react with benzyne. And you get the triflate anion, which, because it's a really good leaving group, it's a really bad nucleophile. So it can't add to the benzyne. So then we can add other nucleophiles.
Would it be possible to isolate the benzyne making it this way?
No, it'll dimerize with itself, or it'll fall apart, or it'll react with, like, you know, oxygen in or water like in the air. You can, for these, you could get benzyne and you would be able to like get spectra of it. You could take like an NMR and see, hey, I have this thing in solution. But over the course of time, you'd actually watch the NMR change as it reacted with itself or otherwise decomposed. So you could observe that it's there, like you can see it, but you can't like put it in a jar. So I should also point out, where does F minus come from? The best way to get fluoride is through something called TBAF, and we'll go over this in more detail later because we use it later on. But it's tetrabutyl ammonium fluoride. Ammonium fluoride. It's the version of F minus. It's the thing that gives you F minus. It doesn't also melt your bones. We'll talk about the other one later. The only thing I was really scared of to use in grad school. HF. It just melts your bones. Sad times. From the inside. Like your outside's fine, but then your bones just melt underneath. Boo, hard pass.
The question was, why does the triflate and the silicon have to be ortho to one another?
So the reason they have to be ortho to each other is for this second step, right? Is if you have to have the leaving group right beside the silicon. So when its electrons come down, right, it pushes this out. This is kind of like an elimination from like organic 1, where you have to have, I want to go over a slide real quick. I'll come back. Where if you have leaving group in your hydrogen, right, and you add a base, right, you grab the hydrogen, those electrons come down and push the leaving group out to make the double bond, right? Right, if you have your leaving group and your hydrogen is over here, right? When your base tugs on this hydrogen, right, there's no place for those electrons to go, right? There's no group for them to push off because that leaving group is now too far away, right? And it's the same thing here. These electrons have to have a place to go, and the only way they can like go to another carbon is they have to have something to push off that carbon. So the triflate has to be beside it so it can push it off. If they're meta, then those electrons can't get to that leaving group to knock it off. So what we can do with this is, so let's say you have your triflate, you've got your trimethylsilane, you can add TBAF as step 1, and then you can add carbon nucleophiles, stuff like, oops, didn't work. And you can end up adding just carbon chains to your molecule. So you get your benzyne, and then methyl magnesium bromide, right? Or sorry, in this case, ethyl, right? MgBr, right? Magnesium is a metal, so we can do our trick where we just say magnesium plus, carbon minus. That negatively charged carbon is going to add to the bottom. So I had drawn over there. Adds to the benzyne, kicks electrons up. Right, you get this negative charge, and then you add the H plus at the end. You pick up your proton, and you get your product. Right, so now we can make our benzyne, and then we can pick what nucleophile we want to add, as opposed to having to be stuck with whatever base we used being what we add to the benzyne. we can just pick any nucleophile we want. Usually it's carbon-based stuff. Usually just use this as a way to add carbons. Right, and you'll notice this is the way that I can put a CH2 beside my benzene ring without having to make a ketone first. Yeah, tricky. So let's say I have something like this. Again, I'm going to put them on the same spot. We'll do triethyl this time. It doesn't really matter. Right? Here, I don't have to worry about making two different benzynes, right? I know exactly where my benzyne is going to go. Right? It's going to be between the triflate and the silicon. And then I add my methyl-magnesium bromide. Whoop. And I'm going to end up putting another methyl group on here. So this gives me, I still need to make sure that my benzyne is symmetrical, right? Because again, I can add to either end of my benzyne, but it's easier to know exactly where my benzyne is going to go. So here I can, again, get to just making one product. So we'll do the last way to make benzynes on Monday.